Oh great, okay. So this is what I hope to talk about today, and in particular, this kind of idea about human physiological data, these responses from our body, and then specific application of this idea of applying this like a special case, really a special use case of how to apply this knowledge to our relationship with computational systems and how that might be used to enhance our creative abilities. I'll remember the clicker the next time. And I'd like to start by referencing comments by Dr. Zhu and Dr. Hubbard, and they talked about this idea of the neurobiological master of our behavior, and then just most recently, Jeffrey, Dr. Martin, with his commentary about the shackles of biology. And this kind of idea that, this is just a little bit of an adjunct in terms of the relationship of this topic to Buddhism in particular, and I'm not a Buddhist, nor am I that knowledgeable on the subject. However, what little I do know is that perhaps some awareness of this reference to the master of our behavior, this kind of shackle, or Dr. Hubbard's reference to the snake being in the forest and the experience with the snake, this awareness of the master's influence on our behavior, how this might allow us to more fully experience reality as it is, if we're more aware of the nature of this master. So in particular, let's see here, develop emotional affect and motivational state awareness knowledge. So kind of we'll explore a little bit of this, and the idea here would be to use this knowledge to enhance human to computer computational system interaction technology, and then about how to employ this technology to better support creative endeavors. And so this would be like a little bit of like a thought experiment on how this could possibly happen, these things possibly happen. So when it comes to biometrics and creative processes in particular, you can think of everything that happens to us, like as we go through our day and all the things that we experience, like for instance myself in this room and the way the colors look and the lights here, and the little rustling of papers, that all perception leads to a kind of stimulus in the body, and then this stimulus causes like some physiologic response. There's maybe certain changes that are happening to me as a consequence of receiving the stimulus, and then finally this kind of idea that kind of awareness knowledge of these responses can be used to enhance technologies that we have available to better support creative processes. So just here's a simple example, and in particular, this is just like the consideration of muscles in the face, so like micro expressions in the face. So there's one here, zygomaticus, and when I smile like that, I activate these muscles here and here, and we generally do that when stimulus is more pleasant, and then conversely, when something is unpleasant, we contract here, called corrugator, these muscles right here. Something's unpleasant. So a kind of pleasant stimulus. And a kind of more horrible, unpleasant stimulus full of feedback. Increasing corrugator. So a little, just kind of more context in terms of what I'm talking about. And this, starting with Hume, David Hume in 1740. And David Hume, he was an English philosopher, and one of the things he wrote was this, it's called a treatise on human nature. And he wrote this very important sentence. It's the one here, which is that reason is, and I think he meant kind of our cognitive sort of rational processes, that they are and not only to be the slave of passions, this kind of idea that our rational thought sort of sits on this emotional sea, and this emotional sea sort of directs us one way or the other. And we're kind of on this ship, and we're moved through these currents, and the way the sea carries us has to do with the kinds of things that our thought processes, rational thought process, think about. And so it's a little bit like my neck moving and pointing my head different ways. And then our rational thought processes make up these stories about the things that we experience. And so that's David Hume. And then a little bit later, William James came along in 1884, and he wrote about this idea of emotion. And no one really actually even knows what an emotion is right now. There's at least 3 competing theories about what an emotion is. But James, his thoughts are still quite popular on this subject, and he felt that an emotion is a feeling that results from like the specific, the stimulus that causes a physiological change. You have this stimulus that happens to you, something you hear, something you see or feel or smell, and there's a physiological change in our body, and the emotion is the kind of label that we give that physiological change once we experience it. It's a kind of a labeling process. And then a little bit later, Levinson in 1992, and I threw his work in here because, and Gino alluded to this too, this kind of idea that physiological processes are processes that are shared by people worldwide, and they sit a little below culture and below language and below skin color and all that. And so he investigated these consistencies between the Minangkabau of West Sumatra and then U.S. college students at Stanford, and kind of looked at them and found like amazing similarities between these super diverse groups of people. And then finally, this fellow James Blaskovich, he's out at UCSB, and he has been putting a lot of energy into this idea. He's retired now, but this idea of motivational state, and in particular, exploration of challenge and threat, which is a kind of human phenomena that's unrelated really to emotion. It appears to be a little bit of a kind of an adjunct. Maybe I shouldn't say unrelated, but just the relationship is not clear. And he refers to it as a correlational theme, this kind of idea of motivational states or challenge and threat. So when it comes to human biometrics, there's different kinds of physiological data, and there's biometrics that point to emotional dimension, and then biometrics that define motivational state. So this is work done in 1986. This thing here is called the circumplex model of affect. So it's a kind of 2-dimensional graph, and along this axis right here, the horizontal axis, is this kind of axis of pleasure, displeasure. And then along this axis, this vertical axis is called the axis of arousal. So a vernacular for this is valence. Actually, typically it's called valence and arousal. And then it turns out you can map certain kinds of emotional states on this graph. And so, you can, if you're displeased with kind of moderate arousal, you're either distressed or depressed. And if you're pleased and you're at moderate arousal, then you're more over here. And it turns out that there's physiological measures that you can do that can kind of perform a kind of sort of objective measurement of these things. And for instance, looking at decreased heart rate and electrodermal activity, which would be like skin sweating, like decrease that, you're more here, and up here would be more increased heart rate. Increased corrugator, we talked about that. This would indicate displeasure, and then increased zygomaticus, push you more to pleasure. And with motivational state, it's a little bit more of the measures are a little more complex, but they can still be performed non-invasively. And in particular, there's 3 that are relevant to kind of classify motivational states. It's blood pressure, stroke volume, and vascular resistance. And this is kind of like how, like an indication of how easy the blood can flow through your body. And this is how much blood that your heart pumps with each beat. Like the kind of, the bolus of blood, which is typically around 100 milliliters per beat. And then blood pressure, we all know about that. And so with a challenge response, this would be one where this idea that you're presented with some kind of something that's happening to you. You're faced with something. And if it's something of merit, you'll think that you either have resources to meet that experience, or maybe that you don't. And if you feel that you do have sufficient resources, your response is this one. So it's this kind of mental idea, right, that you have about your capability, and that reflects in this kind of physiological response. So it's what I think about myself in terms of me being able to meet that experience or match that experience. And so a challenge response means that's like an aerobic response that you would have, like maybe if you're on a treadmill. It should be you get little or no change in blood pressure, you have an increase in this amount of blood that your heart pumps with each beat, and then you have a drop in vascular resistance, and so blood flows a little easier through your body. And then a threat response looks really different. It has this kind of spike in blood pressure, and it's a little bit of a drop in stroke volume, like little or no change in stroke volume, but it tends to maybe drop a little, and then a small little or no change in vascular resistance, but the bias is a little higher. But they're kind of very different looking indicators, and so they're pretty easy to track, like non-invasively. And so the final thing here is that we're more inclined to participate in a situation or circumstance if challenged rather than threatened. And I think this work was originally inspired by kind of job screening work, actually. So here's an example of when kind of getting back to this idea of like design, creative design processes and physiological state measurements. Is that if you in the case I'm talking about here is specifically one where we interact with some kind of computational framework. Like there's some kind of computer we're working with, right? So we're interacting with some kind of machine, and the machine would perhaps present the latest design result to you on its screen, or maybe you hear it or something, and there's some physiological change because all stimulus leads to a physiological change. And then the computational framework could then determine some emotional dimension, this circumflex model of affect or motivational state from your body. And then there would be some algorithm which would say, oh, maybe we should take action, yes or no, on the basis of that data. And then the computational framework or whatever may decide that you need to be stimulated. And then it kind of loops like this kind of process. So when we work with computers, this is the process actually that happens. It's called you could think of it as the designer loop. This idea that the computer presents something to you, right, through the speakers or the monitor. It's telling you something, and there's some response, right, that you have to this data here, and then you have this motivational, emotional, cognitive response, and then here you have David Hume. Your rational guidance is sort of sitting on top of this in terms of guiding your thought. You form an idea about what it is you've just experienced, and then you manifest some physiological control, which is either through a keyboard or a mouse typically, or other kind of pointing interface or something, but generally these two things these days. And then it comes back to the interface here again, and then you kind of move in this loop. And this is like how people work with computers right now. This is what happens. And so this is an example of how that works in practice. This is one way an interface can work that senses physiologic data, and it kind of shows an evolution of how this could work. And this is measurements are being performed on the brain, and this individual's looking at the screen here, and then different letters are flashing out on the screen, and then let's say if the person's thinking of the letter W, when the W is presented, this row is presented, and the person's looking at the W, there's a signal that happens in the back of their brain, and they get a lighting in the brain because that column comes up, and when the W comes up in a row, their brain also lights up. It's called the P300. And then because that one lights up and that one lights up, they know exactly where the person is really looking. And so then it can convert this sort of like brain perception into an actual physical result. So I know this might seem a little bit overwhelming, but it's really pretty simple. There's kind of exploration of this idea of like, there's this designer loop, which we talked about here, this whole thing. And then by the same token, there's also this phenomena of the recipient loop, like the designer, right, is doing work for what reason, right? So the designer is typically hired, or they have there's some ultimate destination, right, for the work that the designer is doing. And so that would be the recipient. The recipient has kind of a similar process. They experience the result that the designer created. There's some kind of physiological sensing. There's some emotional cognitive response. There's rational guidance by the recipient, and then the recipient forms an idea, and then there's some physiological control. Except here, it gets broken because the recipient has no ability to manipulate this, and instead communicates through like email or something to the designer saying what's their opinion about what they've just done, and then how they might fix it or modify it. So the recipient kind of just communicates through this kind of slow process by a phone call or email or something, and then it goes to the designer, and the designer does their work. And kind of getting back to this idea of like sort of a special case, like what if you could link the recipient and the designer? So you could have like the recipient could have this physiological sensing and this motivational, emotional, cognitive response, and they could just sort of hang out in here because the computational framework would keep them away from needing to perform some kind of rational guidance. So they stay linked in here, and then the designer also stays linked in here. So it's a kind of high-speed, emotional, motivational state rapport, which is then mediated by the human-computer interface. I know it seems like maybe a little crazy, but there's a lot of examples of this sort of thing that have been done relatively recently, actually. And just a little more context for that. In terms of emotional communication, like computers' communication to humans that's like emotionally based, a few examples here. This is, I think it was one talk at the Mixed Reality Lab, I think Singapore, and they did this work on the Babbage cabbage, which is this idea of empathic living media. So here's like a cabbage that they use acid control in the cabbage in order to control its shade, and then these cabbages grow in your garden and they represent different things, and if the cabbage is this healthy color here, it means that things are probably going okay, and if it's this sort of unhealthy pink, that maybe you've got some family problems. And it's a kind of way of sort of relating to your data, but not through a screen, but through like actual like a vegetable. And then there's this marvelous project here that Mikey Siegel was involved in, and I'm sure maybe even other people here, I don't know, but Nexi at MIT, and this is an emotional robot, and a social robot, and mobile ambidextrous. And both of these computational interfaces employ a kind of like affect to help communicate better to people. And so in terms of like this like back here, like that, like an example is this here. And this was the Democratic primaries in 2008. And so this was John Edwards and Hillary Clinton and Barack Obama. And this was some work that BioPac was involved in to measure certain aspects of human physiology when these independent voters were considering which candidate to consider. And they were listening to little snippets of the candidates, and then we measured corrugator and zygomaticus and a few other things, and here's a data plot. And so this idea here is that you have a politician as like a designer, right? And so they're crafting a message. and they have a certain countenance on stage, and so there's a physiological response by the people perceiving that, and then as the so the politician is the designer, and then the unregistered or the undeclared voter here is the recipient, and so the recipient's physiologic data is being essentially in a position to be able to be piped directly back to the politician in order to have a kind of link occur. And so this was in 2008, and the ability to kind of have this happen at a much higher speed these days, it's actually quite feasible. So a little more context. This is where we are right now with human-computer application interactions in circa this year. So we have pointing interfaces, which is like, our mouse, and then a finger on a touch screen, and even a keyboard. So these are very high speed, short processing time. And then we're getting a lot better at this. This is like voice control of computers and the computer facial recognition, and this kind of stuff is getting a lot better. And even 2 years ago, it was like quite a bit worse, but now it's getting good. And then this human physiological data, which is what we're talking about here, is kind of in the same category as this. It's like, in fact, even a little bit less demanding in terms of its data requirements than audio and video, because most human physiology data sits in this kind of DC to like 1 kilohertz band, whereas audio is like 20 hertz to 20 kilohertz, so it's higher bandwidth, and video is like way higher. And so just that, like we have the tools and capabilities and processing speeds to handle this kind of data. It's just that we lack a kind of, it's sort of new, and it's a little cumbersome to get this data, and it's complex, and we need better feature extraction to look at the salient, the actionable vectors. Like it just needs a little bit more software kind of to get at that stuff. But we've been kind of employing attention here and not so much there. And so what's possible now? Without really speculating too much about the nature of this proposed interface, but what's possible now. So we can establish emotional dimensions, a circumstance model of affect, we can determine motivational state, we can introduce a stimulus, some kind of creative design example on the computer, and then we compare this emotional dimension or motivational state to that specific stimulus. So the biometrics to computer with the things that we can measure electrocardiographic activity, electrodermal, electromyographic, pulse plethysmographic data, respiration, skin temperature, motivational state, this stroke volume, blood pressure, ECG, and then the stimulus from the computer could be all kinds of things. It could be the computer could establish some kind of emotional rapport with you, and a little unclear what that might be right now, but maybe it's a scent, right, the computer releases, or it encourages you to get a cup of coffee, or maybe it changes the music, or the temperature of your chair, or maybe it throws out a hyperlink. And so this is a kind of conceptual example of how this could work. Let's say you're an architect and you're designing something in a building, and this is your mock-up here of what the thing looks like. And so, and a person might be navigating this in some virtual space, right? And so you walk through here, and then when you encounter this range of yellow doors, there's this green chart here, and it's the dip at the point that you encounter these yellow doors, and also there's a drop in valence, and then there's no change in arousal really. But the question is, or the thing is, you're exposed to both of these pieces of information, and so you could probably do something about that if you wanted to, and the computer could be aware of that. This is the case. And then be in a position to be able, the computer could recognize this and then iterate actually for you on this design and be monitoring your changes, physiological changes, as it starts iterating on aspects of this design, and then see if it can encounter one that maybe doesn't have this phenomenon. So how to get physiological data? You can have probes inside of the body, you can have probes outside of the body, and then probes that don't touch the body at all. And these are the kinds of signals you can acquire non-invasively, these like biopotentials, these biomechanical signals, and these biochemical signals. This is how standard non-invasive measurements are performed, and whether they're either wired or wireless, they all involve often wires on some level. in terms of attaching electrodes and whatnot. And there's some conveniences in terms of getting things closer, but this is kind of how it works. And there's a movement to this wearable technology, which Jeffrey had a marvelous slide on. And then emerging technologies like functional near-infrared imaging, which is like a poor man's MRI. It kind of looks at blood flow in the brain. And then new work out of MIT and, at MIT you see Larian imaging, where it can use cameras to detect changes in blood flow and heart rate. And then also microwave Doppler radar systems that can measure respiration and heart rate at a distance with multiple people in the same room. And these are the kinds of fully non-contact measurements you could do that, in addition to the Doppler radar, you learn imaging, but you could look at CO2 levels, these scent in the room, heel-toe strikes, gait, weight, and certain kinds of biochemical analysis. And then really new work that maybe like things like electronic tattoos, which I imagine we'll start seeing more of, and then or these ingestible biosensors. So I'd just like to end with this simple example, and this just touches lightly on Gino's comment about this idea of life as possibly considered as this like dance to our perception of the reality of it. Should be working, but okay, I guess we're not going to get that. Leave that for another time. Right, thank you.